For just a fast recap of the chapter capacitors and electric field, these are the stuff that we have to learn. Equals to K R squared, electric field strength. It is a vector. Also a vector which is force binding charge is equals to K Q by R squared. Voltage scalar is given by work done per charge from infinite distance or energy required per charge. This E scalar is the energy, so not to confuse with the electric field strength. It's given by KQ by R. We've also seen the graphs of multiple different charges placed side by side. What happens for the electric field strength and the voltage distribution for charge particles for the space in between them. We've seen it for one charges. We've also seen it for spherical charges. So I'm not going to draw those graphs. That's detailed forms aiming. What we've also learned for the capacitor parts is that the capacitance of a certain capacitor is given by charge over voltage. So this is the unit of farad, which is equals to coulomb per volt. This basically means that how much charge is required to maintain unit potential difference across the two plates of a capacitor is defined as a capacitor. Capacitor does never store charge; it actually stores electrical energy, because in any case, any capacitor will always have equal amount of opposite charges on its own both plates. So the total charge stored in a capacitor is always zero. However, whenever we use the term charge stored in a capacitor, we always refer to charge stored in one of the plates. That is, what is the magnitude of the charge in one of the plates? So how much difference have we made? But in true sense, capacitor actually never stores charge. But for the sake of easier understanding, easier explanation, we use the term charge stored in a capacitor Q. This always means charge stored in one plate of the capacitor is Q. Then we've also seen that for whenever the capacitor is charged, all the three variables. So for charging cases, whenever the capacitor is charged, for charging cases, all the three variables, initial current, charge stored, and the voltage, they all start from, sorry, not that, not current. Where is this thing? The charge and the voltage, these two variables for the case of charging, they go up exponentially. So initially we have a pretty high value, and then the value slowly decays over time. So this is somehow looks like this. So this is the maximum value that it can get. For the charge axis, this is Q equals to C into V of the source. For the voltage axis, this is just the maximum supply voltage of the source, and this is time t. Ideally, this line is supposed to become asymptotic with this dotted line. This is the maximum value we can take, but for practical purposes, we can consider at certain point that difference is nearly zero, so we can pretty much merge these two lines together. And as for the charging graph, the current, however, changes a bit differently, because initially the current is pretty high because the charging happens pretty rapidly, because the stored voltage in the capacitor is very small, so it doesn't oppose the charging EMF pretty strongly. But as time goes by in the charging process, the capacitor starts to build up its own voltage, taking charge from the source, so it starts to oppose the charging voltage or the EMF of the source. So that's why for the current value, this actually starts from a pretty high value and it slowly decays exponentially to zero value. So it's actually become asymptotes, but well, we can say zero anyway. So these are the shape of the two graphs. You don't have to know the equation of these two graphs. These are just the shapes are introduced in the syllabus. So I'm not going into the shape of these things. However, discharging graphs has a pretty large discussion in our syllabus. So for the discharging graph, the idea is very simple. If we plot any of these three variables, I'm going to write x with respect to time here. The x could mean either the current in the circuit, it could mean the charge stored in the capacitor, it could also mean the initial voltage of the capacitor. So if we have the value starting from x naught, it always takes a negative exponential decay graph like this. It just so happens that the value of this graph, x equals to x naught e to the power minus t by RC. So this is the equation that this discharging graphs follow. It can be for current, it can be for charge, it can be for voltage. The naught value represents the initial starting value when t equals to 0. As time goes by, all the three values, current or charge stored or voltage across the capacitor, they all slowly decays down. However, one thing that we need to appreciate is that RC is what we call is sometimes represented by tau, and this variable is called the time constant of a circuit. You have to understand this is not a property of the capacitor itself. This is time constant of a circuit. The reason we use the term circuit because we have the R involved here and C also involved here. So R comes from the resistance of the circuit. This is basically the total resistance to the capacitor is discharging. This is usually comprised of the external resistance of the through which we call the sometimes called the load resistance. And if the capacitor has some loss within itself, which is somewhat similar to internal resistance for a battery, that is also going to be included over here. However, for your syllabus, we do not consider the internal resistance of a capacitor, which is actually not internal resistance. Sometimes we also use the term inductance, but that's not very detailed discussed in your syllabus. So we're going to consider all of our capacitors for the upcoming discussion and for your problem solving cases, that all capacitors will be considered to be ideal capacitors, which means they don't have any built-in resistance towards something similar to the internal resistance, or they don't have any inductance whatsoever. So tau basically represents the amount of time after which the initial value reduces to 37% of starting value. So this actually means this is somewhat similar to half-life, because this is also negative exponential curve. In the case of half-life, or what we've seen in our AS level, also in our O levels, that for half-life, the initial number of nuclei, undecayed nuclei, radioactive nuclei, or the initial number of mass or initial activity of a certain radioactive specimen, that actually becomes half every fixed amount of time. So it becomes, so in that case, that ratio value is actually 50%. So the amount of time within which for a certain radioactive isotope or a specimen, the number of undecayed nuclei reduces to 50% of its starting value. That amount of time is defined as half-life. For a capacitor, it's not 50%, it's 37%. Now, where does this 37% is such a random number 37% comes from? It's actually not random. What I can show you is that if we consider that a capacitor is starting to decay and decay and decay, we want to find out that after how much time, let's say, what is the amount of time after which not necessarily that. What I'm going to do this, the way we can do this is that when tau amount of time, so let me just write down, when tau amount of time passes in discharging process. So let's say we do not know how much time is tau. So we're trying to define the tau value. So that's what I'm trying to show you. This is sort of a bit of a reverse calculation, so it might look a bit weird, but that's how it has been defined in our syllabus. So bear with me. When tau time passes in discharging process, the remaining value of x in this case could mean I or Q or V, is how much? Actually, I could not construct that question very well. I should have started from the how much part, but anyway, what I'm trying to show you that, let's say we are starting to discharge a certain capacitor circuit through a certain resistor. Maybe let's say we have a capacitor that is charged to, let's say, 10 volt positive plate, negative plate, and then we have a certain resistor over here. Let's say that resistor is R. The capacitor has a capacitance of C. We can assign values to all of these, and then we can go down. Let's say we have a switch over here, which we're gonna close and start a stopwatch by some computer mechanism, because manually it would be very difficult to do. It's not impossible, but it's difficult to do to have a precise measurement. And then we want to calculate that when tau amount of time will pass, what will happen to the charge stored or voltage across the capacitor, or the initial current that happens. So if we want to measure current, we might also consider to introduce a certain ammeter over here. In many cases, we use milliammeters or micrometers. If the current is supposed to be very small, that can also happen depending upon the voltage of the capacitor and the resistance. So if we have a resistance that's within the kilo ohm range, and the capacitor is charged within the voltage range, using a milliammeter might be actually a good choice to get a more precise reading. However, so if this amount of time passes, so that can be calculated. Let's say if I go for the calculation for, let's say, remaining voltage can be given by V naught into e to the power minus T by RC. So if tau amount of time passes, this T will actually be tau. So we're trying to find out what would be the value of this one when tau amount of time passes by. So if I replace this value over here, V naught into e to the power minus tau by RC, it just so happens tau is practically RC. So we're gonna get V naught into e to the power minus 1. This is basically V naught into 0.37. So that's pretty much where we get V equals to 37%, nearly 37% of V naught. The same thing can be represented for Q for current I. So I can also write in the similar manner that Q should be also equal to 37% of Q naught, and also remaining current should be also 37% of initial current I naught. Now 37% is a 2SF value. If you just use a calculator and use e to the power minus 1, the constant E is on the ln button. If you look up in your calculator, there is a yellow e to the power x written over here. So if you press shift ln, you're gonna get the E sign in your display, and then you write minus 1, and that's gonna give you 0.3678 something. So that's rounded up to 2SF, we get 37%. That's how we define the time constant of a circuit. The time constant of a certain capacitor circuit is actually pretty important, because that controls the many of the usage of a capacitor, which we're going to see in a much more detailed version for the application part. But what I want to understand that this constant tau is dependent upon two factors. It is dependent on the resistance. It is also dependent on the capacitance. What I want you to understand that if the resistance of the starting capacitor is large, then the tau would be also bigger, which means it's going to take longer time to discharge. So if we try to compare two different circuits over here, let's have a look over here. Let's say we have a certain capacitor, which will be, let's consider two capacitors side by side. Let's say this is capacitor 1. So capacitor 1, this is capacitor 2. And let's say this capacitor has a starting voltage of plus minus V. This is the starting voltage, so I'm going to keep plus minus V over here. And this capacitor also has a voltage of, let's say, plus minus V. And we're going to drain this capacitor through a resistor R over time through a switch, of course. We are going to need a switch. And if we are trying to measure the current, there should be an ammeter as well. I'm not drawing this over here just for the sake of simplicity. And let's say if we want to drain the same capacitor charged by by the same voltage from the same source, maybe if you want to discharge it through a resistor that has double the value of R, then how these two graphs are going to differ from each other? Here's the thing. Have a look. I'm going to draw both of these graphs in a single axis system. So have a look. Let's say this is the voltage versus time graph. So what we're trying to draw over here, as we close the switch, how does the voltage across the capacitor, which you can measure by the use of a voltmeter. So a voltmeter might be in place. So let's say we have a voltmeter. How does the value of the voltage across the two plates of the capacitor changes as time goes by in the discharging process? That's what we're trying to get at. Now, important for us to understand, is that let's say this is the starting voltage of the capacitor of both the capacitors. Let's say this is our V naught, which is same for both of them. If the first capacitor, let's say it has a capacitance of RC. This circuit has a tau value of RC. However, this circuit has a tau value of 2R into C. So this is double the time constant, which basically means the amount of time by which this circuit is gonna take to reduce to 37%. So this is the curve. So I'm gonna assume approximately 37% of this value. This is 100%. This is 0. So 37% may be somewhat over here. This is 50%, about somewhat over here. I'm assuming this place. So this is the 37% value. So if this capacitor takes this much time, this is the value of tau, which is equals to RC. The second capacitor, which has a time constant of double, is going to take double the amount of time. It's going to drain slowly because there is a bigger resistance. It's going to allow the charge to flow out slowly. So it's going to drain slowly. So it's going to take longer time. So in other terms, you can say that it's going to hold up your voltage. It's going to hold on to its voltage for the double amount of time. So simply, for the sake of drawing this second graph, I can simply double this time constant over here. Let's say approximately over here, and take out this extension right over here. I get about this point. The second capacitor is going to discharge in the same negative exponential manner, but it's simply gonna take double the amount of time. So what I want you to understand, both all of you, that this is your starting value. This is your 100%. This is your time constant related value. This is 37%. The capacitor which has tau equals to RC, if it takes this much time, the capacitor which has a time constant that is double the amount of time, twice R into C, that is going to require double the amount of time for its 37% drain. So it's going to discharge slowly. This is one way to explain this process. If you wonder that what other variations can be there can be a lot of other variations. The thing that I just told you a little bit earlier, that if you have a look over here, this time constant is actually dependent upon two factors, R and C. So both the variables, resistance of the circuit and also the capacitance of the capacitor, attributes or adds up or works towards the controlling factor for the time constant. So it's easier for us to understand and also for me to explain if we take first one variable at a time, then you go for the simultaneous change for both the variables. So what I'm trying to show you over here, let's say both the capacitors were charged to the same voltage. Both the capacitors were having the same capacitance because I have used the same capacitance C for both the capacitance over here. So C1, C2 in this case were considered to be identical capacitors. Only for this graph, I have considered the resistance of the capacitor has been what? This one has R resistance and this circuit has 2R resistance. So this is the variation that we consider. The other type of variation that we can have is that, let's say, if we have V and R same for both the capacitors, however, if we have a difference of C, so let's have a look at that thing. I'm going to go through these graph variations because graph variations can prove to be a very important part for your theoretical discussion questions. And teachers can actually set up a lot of different variation of questions, although it is not very highlighted in the syllabus. But in my opinion, these graphs of the voltage versus time graphs for the discharging variables, it falls within the shadow region of the syllabus. I mean, if the teachers want, examiners want, they can set up really never seen before type of questions for you, and you cannot say it's not in the syllabus. It's definitely in the syllabus. So whether you understand it or not, it's gonna fall onto your shoulders. So I'm gonna try to take some time to go through in detail for what this happens. The school teachers, or if you are going to any other physics teacher, they might tell you that this is not necessary. I can totally agree with them. This is not exclusively explained in the syllabus, that students should be able to do this thing. I personally feel that students should be able to do this thing because difficult questions can be set from these graphs. If I was making a say question and or let's say if I was trying to judge the actual capability of a certain student's understanding level, not essentially mathematical capability, I might set some pretty interesting question using these graphs. So that's why I want to explain this thing in detail. So let me try to draw another circuit, another setup. Let's say we have two capacitors. Oh, by the way, One thing that I would like to mention, should I would say, before I move on from this curve, is that charge stored in a capacitor is given by C equals to Q equals to CV. This is the amount of charge stored for a certain capacitor. In this case, we consider the capacitance to be equal for both the circuits, and the initially charge voltage was also same, which means at the beginning, at t equals to 0, both the capacitors will have the same amount of charge as well. Both the capacitors will have the same amount of charge. So before I go on to the second graph, there is a certain part that I would like to show for this graph. এটা এখানে থাকুক, আমি এখানে এই ডিসকাশনে আরেকটা গ্রাফ আমার এখানে আঁকা লাগবে, কারেন্টের গ্রাফ দেখাতে হবে, দেখাচ্ছি, hold up. So both the capacitors will have the same amount of initial stored charge because both of them has the same C, both of them were charged to the same initial voltage. So the initial charge Q naught should be exactly same for both of them, which means this graph of V versus T could be also equally reciprocated, or not reciprocated, it could be equally used for the shape purpose for the Q as well. So in this case, if you are going for Q, this variable is going to be Q naught, and you are going to have Coulomb versus time graph. Second, so this can work just fine. But what about the current factor? The reason we are talking about these three variables, have a look, because this equation of discharging equation, have a look. This is x equals to x naught a to the power minus t by RC. This equation for a discharging capacitor, this x can have all the three values. It can be used for current, it can be used for charge, it can be used for voltage. So we have to talk about all the three variables if we're trying to show some discharging curve with respect to time. So up till now, what I'm trying to show you is that the voltage is going to decrease nearly exponentially like this format. Current is a charge stored in the capacitor is going to discharge in this format. What about the current? Now, one thing that you need to understand, current of a certain capacitor is actually defined by Ohm's law, which is given by I equals to V divided by R. Try to understand. We have two different circuits over here. What we considered that our first circuit has a resistance of R. It was charged to a voltage of V. The second circuit has had a resistance of 2R. That was also charged to a value of initial voltage of V. I can actually give V naught over here just to make sense. They are both charged to the same voltage. This necessarily means if we're trying to get the value of current, let's say initial value of current for